Okay, so in this video we're going to take a look at different reactions. Given the number of moles of reactant, how many moles of product are produced, and just a reminder of all the different mole conversions that you should be comfortable doing. For solids and liquids, you need to be able to convert from mass to moles using molar mass. For liquids, you need to be able to convert from volume to mass to moles, again using rho density and then using molar mass. For solutions, you need to be able to convert from concentration and volume to moles using the formula concentration times volume. And for gases, you need to be able to convert given the volume, temperature, and pressure of a gas to determine the number of moles, again using PV equals nRT. So you should feel comfortable with all of these different calculations because what we're going to be looking at now requires all of the numbers to be in moles. So take a look at this reaction. I have a pencil turning into a broken pencil, and I've created a table where we have the initial amount, the change, and the ending amount. I've started out with 100 pencils. I am changing those 100 pencils into broken pencils, so negative 100 and then positive 100 to show they're turning into that. And at the end I have 0 pencils and 100 broken pencils. That is my theoretical yield. It's how much I should theoretically get. If I actually do this in the lab, for example, there might be some sources of error, some of the pencils might get lost, etc., etc. And so maybe my actual yield is 90 pencils, and so I can calculate my percentage yield to be 90%. I only produced 90% of products that I should have produced. Here I have another example, but this time using chemicals. So here we're turning glucose into an isomer of glucose known as galactose. Here I'm starting out with 0.200 moles, and I'm going to use all of those up, so I'm going to change by minus 0.2, and then my galactose is going to increase by 0.2, and I'm going to end up with 0.2 moles of galactose, again as my theoretical yield. Now again, let's say I do it in the lab and I actually only get 0.09 moles when I do the experiment. I can calculate my percentage yield as being my actual divided by theoretical, and that's 45%. So I only got 45% of what I was supposed to get. Again, taking a look again at another analogy, here we have a bicycle frame plus 2 bicycle wheels turning into a full bicycle. Here I'm giving you the initial amounts, initial amounts, and again the change of the reactants is always going to be negative and the change of the products is positive. And so again, because I'm in a 1 to 2 to 1 ratio, even though I have 300 wheels, I'll only be able to make 150 bikes because I use 2 wheels per bike. Similarly, if we take a look at a chemical reaction of iron oxide plus aluminum turning into iron plus aluminum oxide, again, this ratio is not 1 to 1 like the broken pencil. Here it's 1 to 2 to 2 to 1. And so given my initial mole amounts, I can figure out how many products will be produced. Here I have 15 moles of iron oxide and 30 moles of aluminum. I'm going to use all of those up and end up producing 30 moles of iron, again because it's in a 1 to 2 to 2 ratio. Now assuming I produce 30% in the lab, I have 100% yield here. One last example with the bikes. So again, I have a 1 to 2 to 1 ratio where we need 1 frame for every 2 wheels. This time though, my initial amounts are a little bit different. I have 150 frames, but 9,999,999 wheels. And so hopefully you can see that if we were to use up all of the wheels, we wouldn't have enough frames. So using up 500,000 wheels would not be feasible because I only have 150 frames. And so in this case, the wheels are known as the excess reagent because there's more than enough to produce how many products we're going to produce, whereas the frames are known as the limiting reagent, the reagent that's used up at the end of the reaction. And so again, at the end, I will end up producing 150 bikes, even though I have, 9 million frames. And again, if I get an actual yield of 135 bikes, you try calculating the percentage yield. So we can do that same analogy of excess and limiting reagent with actual chemical reactions. So again, back to my iron oxide plus aluminum reaction. Here initially I have 48 moles of each substance, and what I'm going to do here is I'm going to do two scenarios. I'm going to do a scenario A and a scenario B, and I'm going to calculate the change in end moles for each scenario. In scenario A, I'm going to use up all of the iron oxide. So if I use up all of the iron oxide, I'm going to use up 48 moles, which means I'll need to use 96 moles of aluminum because of that 1:2 ratio, and I'll end up producing 96 moles of iron. In scenario B, I'm going to pretend that I'm using up instead all of aluminum, so I'll use up all 48 moles of aluminum and end up only using 24 moles of iron oxide, again, 2:1 ratio. For calculating the end moles, you'll notice something particular. In scenario A, we have a negative ending amount of moles. That's impossible. We can't end with negatives amount of moles. So scenario A is impossible, so I'm going to cross it out. That's not what will happen. What will happen is scenario B, where I produce 48 moles of my product. And again, taking a look at the end amount, you can identify both the limiting and excess reagent. And again, I have 100% yield in this particular case. Now, just a reminder, taking a look a little bit closer at percentage yield, theoretical yield is the number of moles that you should get based on calculations. So based on any calculations that you did, given the starting amounts, that's the theoretical yield. The actual yield is based on experiments in the lab. So you actually have to perform the experiment, and again, this will rarely be 100% because a lot of small systematic or random errors. To calculate percentage yield, we divide actual by theoretical and multiply by 100. If you get a number between 85 and 100%, that's good. If you get anything lower than 25% yield, it's pretty painful. And then if you get above 100% yield, there could be a lot of different issues. You could have an impure sample, it could still be wet, you could have done your calculations incorrectly. Okay, and just to show you how much percentage yield affects the outcome, if, for example, we have an average of 50% yield for a 10-step synthesis, so something that takes 10 steps to produce, what will happen is that the amount of moles that you start out with will be greatly reduced. And so to calculate that, you can multiply the amount of moles you started out with by 0.5 to represent that 50% to the 10. And that results in an extremely lower amount of moles than you started out with.